That must go there. And that goes there. Yeah, that does. That's it.
Gulliver's Laws.
That must go there. And that goes there.
That's right, that must go there.
Royal Institution Christmas Lectures. Lecture 2, Meat and Drink Sufficient.
I'm going to have that bell soon. I'm getting worried. I have to perform. Okay, would you mind sitting down now? We might get started. I begin again with another page from our text. In the last article for the release of my liberty, writes Dr. Gulliver, who was under some trouble at the time, as you may recall, the emperor stipulates to allow me a quantity of meat and drink sufficient for the support of 1,728 Lilliputians. Sometime after, asking a friend at court how they came to fix on that determinate number, he told me that His Majesty's mathematicians, having taken the height of my body by the help of a quadrant, and finding it to exceed theirs in the proportion of 12 to 1, they concluded from the similarity of their bodies that mine must contain 1,728 of theirs, and consequently would require as much food as was necessary to support that number of Lilliputians, by which the reader may conceive an idea of the ingenuity of the people, as well as the prudent and exact economy of so great a prince. The Prince of Lilliput was not the first, nor was he the last ruler to have bad advice from his scientific council. The mathematicians of Lilliput were not right. Indeed, they were right in their geometry. Yes, we discussed the geometry last time, and I think all will agree that they understood Euclid, and they understood proportionality, and they understood scaling in respect to geometry perfectly. It is quite true that the man-mountain Gulliver, being 12 times as high, and proportioned similarly in all parts to a Lilliputian, would be 12 times 12 times 12 as great in volume, or 1,728, and the same amount greater in weight, since he was made of the same material, bone and flesh, similar proportion in all respects. That is the assumption of the text. But where they failed, of course, to be quite right, was when they said, consequently, he will require 1,728 times as much food. The consequently is very much open to question. Why is it consequent? Euclid said nothing whatever about eating and drinking of spheres or polygons. That's a physical problem, a biological problem, a problem of energy, chemistry, the shuffling of atoms, and we have to study that in a much more detailed way. Now, that has been done. We shall do some of it here today and see it ourselves, and I think we can come quickly to the conclusion that the Lilliputians were in error on that small point, but that's not the interesting thing. The interesting thing is how remarkable will be the result that is the real result in the real world, which I think goes far to illuminate how we understand ourselves, the animal world, our structures, and so on. Let us first look at a simple example. If we have the map, Bill, please. Thank you. Just to use a very early example of which is a quite familiar geometry, mention it quite quickly. Here we have these two countries. I've drawn it with the shrunken Atlantic. Possibly we're drifting that way again, I don't know. And with the shrunken Atlantic, so you can see the two simply in their proper proportions, in their proper scale. Now notice, if I ask how much coastline or edge, perimeter, Britain has for each unit of area, there's really a good deal. Nobody can be very far away, and every square of area can possess an edge on the sea in quite small squares. But if I make squares of the same size in this big country, I leave a great section of the country far from the sea. The squares in there of a size to fit neatly in Britain would be nowhere near the sea. They have no coast at all. This region contains, for example, the state of Nebraska, like Switzerland without any seacoast. I shall refer to it from time to time. Western movies are often made in western Nebraska and eastern Colorado, far from the sea. And here we have the United States and Britain drawn on a scale more nearly equal. And now you see the same effect begins to appear. Even though the shape is quite different, still it would be true if I make squares which have edges that are coast. Many squares, little pieces of coast, many squares would be far from the sea, here as here. Indeed, the larger the area, the less surface, the less edge it has per unit area. Let us do that a little more formally on the board and with our blocks, and we'll see how it can work. Let us first work, I shall first work and discuss the problem solely in the flat plane, just to make it easy enough. Now, clearly the world is not flat. The world is not flat in any part. It is our symbols which are flat. Even paper, as we've seen, has plenty of thickness and plenty of scale. But it's worthwhile to work first in our mind in 2 dimensions, just because that's easier than 3. So I'll speak of the flat world as I speak of a flat map. In reality, we shall very soon have to go over to the solid bulk. But looking at the flat, then you can see that around a block there are 4 edges. Around a square, the face of a block, there are 4 edges. Every square owns the same 4 edges. And only if I amass many together do I begin to see that there are some blocks like Nebraska or like Switzerland which are isolated. Let us write down what that leads us to. If I have a square, I'm not sure how you write what you call the distance round, the region round. I will call it the coastline, if you like. If your more fancy word is perimeter. Now the perimeter is proportional to the size of the edge. If that is L, the perimeter of a square is 4L. If it's a circle, it's a different formula, but it's still proportional to L. If I take 2 blocks and make one just double the size of the other, you will quite agree I get twice the perimeter if the shape remains the same. That's the proof. So the perimeter is proportional to L, a straight line curve. On the other hand, the area, all that, is proportional to L squared. Again, the same argument would work. So you see, if I simply consider bigger and bigger L's, 1, 2, 3, I would get 1, 4, 9, and clearly this is going up faster than this. This is going up only as a straight line, this is going up as the square. So the amount of area per unit perimeter is always increasing the bigger the object is, without any change of shape. And of course, for a smaller object, what happens? Just the reverse. The more perimeter for the little bit of area. And the same thing happens in the 3-dimensional world, as I say, where I will now discuss the surface, which is proportional to the square of the dimension, and the volume, which is proportional to the cube of the dimension. Again, this goes up faster than that. And indeed, if you wish, you may work out the ratio of these two and see how it goes, and you will find that the ratio, there's more volume, more surface per unit volume as you get smaller and smaller, just in the ratio of the sizes. One power cancels out, and the others remain. Now, that is the fundamental mathematics of all that we'll do this afternoon, and I think it is not taxing, but it must be carried beyond geometry. That's the key, and that's where the mathematicians of Lilliput had not had the 200 years of history of science since, so they were not able to do this as we can today. Let me look first at an example in the real world, to show you an example in the real world of, I think I can just move this forward, not to worry, of another way, however, of changing the area. Possibly when you watch the map of Britain, the map of the United States, you notice there really are 2 differences. Not only is one larger than the other, and therefore this straightforward effect of scale arises, but also Britain is much more infolded. The arm of the Severn comes in. the arm of the Thames comes in. The great fjords of Scotland come in. And America, except in New England and perhaps near Florida, is much less indented on that scale. That is another effect, because if I am constrained by size and I want to make more surface, I have only one choice. If I can't change size, how can I make more frontier, more surface, more boundary? I can make the edge jagged instead of smooth. The jaggedness adds surface going back and forth without adding area, and that is very frequently done and visible in all scales in the real world, as I think we can now demonstrate. Here is a familiar aerial photograph of a familiar part of the world. It is the island of Manhattan, highly populated island of Manhattan in New York. Notice the Hudson River and the East River flowing together at the Battery. And up and down each side of the island and across the rivers, you see this fringe, which is, speaking broadly, an indentation of the land. The land has gone out, sending fingers out into the water. All over the island, it's fringed. Why have they done that in Manhattan? What do they want?
To bring more ships in, docks.
Yes, and those are docks. They bring in ships. Speaking in a geometrical language we've used, what have they made extra on the island? Yes, they've increased the perimeter in 3 dimensions of surface, exactly so. And that's a very powerful method of doing so when you can. They couldn't change the size of Manhattan Island, so they sent out these digits or spines or spikes, whatever you want to call them. That's been done elsewhere too, and possibly not quite in the same way. And we shall talk about it. We want to see that first on a very different scale. And Bill, perhaps with the microscope you can help us do that. Meanwhile, we're going to look at a microscopic scale several times, and Miss Hardy will again show us the stereo scan, and this time I think we can explore really deep scale with stereo scan. Now, when you have given us the microscopic view, Bill, we can take down the lights, and we'll see a tiny scene on the microscope, not a large aerial photograph, but a tiny scene. And that scene is, of course, a microscopic photograph. Now, you may say it looks very much like a sub-Lilliputian picture of the docks of New York, but it is not at all, of course. It is a section of the lining of the human stomach, where, again, there must be a contrivance to increase surface, because what is wanted is absorption of material across the surface. The more surface, the better that can be wrapped in there, and therefore these things, which I think are technically called in the Latin villi, have been formed. They're very small. The whole distance across that circle that you're seeing is 1/2 millimeter, about the size of a big full stop in letterpress. Thank you, Bill. I think we can have lights. And it looks just like the docks of New York, I submit, and for much the same reason. Now, here's another method of getting the same effect by a different style of geometry. Let me just make the drawing, and we'll see how it goes. There's more than one way to indent a line, or if I speak in 3 dimensions, to convolute, to make complicated a surface. If I take a line, I suppose this is land up here and water here. I wish to have more surface. I do what the New Yorkers did, extend out a pier from the land, many piers. I had that earlier today. Opening the pier up to the land, and now I have a little more land, but a great deal more surface. You see, in a way, the typical size of Manhattan has become smaller. The typical size of Manhattan is like the size of the dock, the square like that. You could think of it as a way of making your region effectively smaller. But of course, that's not the only way to increase the water surface. I could equally well simply let the water into the land. That doesn't make any difference. It just depends which I wish to do for other reasons. Scaling never gives us all the reasons for a phenomenon. It gives the sort of the overall control. But the details depend on looking more specifically at the engineering, the biology, or the physics of each individual case. So here we have water into land, here land into water, and that has been done, and not so far from here, quite beautifully. Here we have an aerial photograph again, the same sort of thing. Sorry. The Surrey commercial docks, south of the Great Bend of the Thames, after the Pool of London, and there you see the same thing. The water has been extended into the land, making a much larger Thames bank, if you like, than the Thames bank would have had if we had simply moved along this smooth curve. You have to count all that as Thames Bank now, and it's very much longer. A much larger perimeter has been made. Now, this is found to be true not only in docks and the internal lining of the stomach, but in innumerable biological contexts especially, because organisms, above all, depend upon having their way of seeing, of having interaction with the world. They must take in air or food or water. They must give out wastes or heat or gases. And all of these things demand surface. Therefore, they can't change their size easily. So they struggle to change their shape to have surface. And I show a succession. The fir branches, these beautiful needles, which add much more surface than a much more regular geometrical spherical shape might do. The coral, which is doing exactly the same thing. Surface for the seawater to penetrate deep into this enormously branched and difficult region. No geometer would be very happy to try to calculate from the dimensions what the area was here. It has to be done by detailed approximations of the shape. And the same thing is true, very more familiarly perhaps, in this beautiful example of English lawn, carefully nurtured in the Royal Institution for Christmas time. This is not a small matter. The sunlight and the exchange of gases is indispensable for the life of the plant. How much more surface it gets this way than if we're all rolled up into a little green pod, a spherical pod sitting on each root. You might calculate that for yourself sometime and see how much the gain is by dividing it into this beautiful peninsular sort of structure. That's the best I can say. But now we can see this also, and here's another sea animal, which shows the same thing, a sponge, a very familiar sponge. And again, if I open the sponge, his section looks again the same. Within, he has both the London and the New York solution, I would say. Interior and exterior surface change. So that is reasonable. And now I think we are probably in a position to look at a really detailed examination of a tiny surface. And here I show the familiar luncheon tomato, and I only want to call your attention to the little seeds that always occur. We're going to look at a close relative of one of those seeds. The tomato has seeds a few millimeters across. Now, in the stereo scan, have we got an image? Very good. We have an image which we will go through as successive magnifications of a dried seed, very similar to the seed of a tomato. It is a seed of a plant of the same family, in fact, and I expect that a tomato seed might look very much like this, though I have not actually looked. This one is mounted and dried and being probed by the electron scanning beam, and now I think if the lights can go down, we can see this seed of the plant of the same family, the nightshade family, there on the screen. The rapid flicker is, of course, the scanning beam interacting with the television chain. And you may notice the apparent trembling, shimmering motion on the surface of the specimen. That is not, of course, an actual motion of the specimen. Nothing moves. It's just a kind of electronic shimmer. We'll look at it more and more detail. Notice the roughness, and again, and once again. Is that about 200 times? It is 200 times. At that point, we're looking at a ½ millimeter. You see, it's the same size as the magnification of the stomach structure. You notice there's an enormous detail. It looks like a rough landscape. And now we can take our moon landing capsule in inner space down farther and look more closely at this landscape. Up it goes, still rough. And again, and again. And now we're at 2,000, thank you. Now we're at 2,000 magnification. That's about as much as good optical microscopes can expect ever to do. And you see there's plenty of rough structure and plenty of surface being formed there out of the material. It hasn't reduced itself yet to a bland, round, featureless surface. Let's keep going as high as we can go. And of course, we begin to lose detail. Whether because the detail is actually not present and the surface is smoothing out, I think we keep on going. Or whether because it is simply the beam of the microscope is becoming too coarse to probe the very fine surface, I am not sure. But this is an example of what you see in almost every biological system, an enormous refinement of surface roughness at almost all levels. There we have, what, 20,000 magnification? Those details are probably 10 to 20 times smaller than the finest details to be seen with an optical microscope, and they're seen in the surface of an ordinary plant seed. You can imagine every object we examine of biology has this remarkable intricacy, very often showing, not always, but very often showing as a rough, complex, spiny, or pitted surface. Thank you very much. Splendidly. It's very hard to see anything smaller than that. Now, it is not merely the geometry that we must look at, but again, as I have said all the time, we are trying to see how things work. And a rather spectacular way of showing the relations of heat transfer and of energy change can be made if I heat this Bunsen up a little bit. Here's a bar of metal. Now, everyone knows you can't take a solid bar of metal and burn it, and you will not be surprised when I put it in the good hot flame, nothing happens. But if I take a ribbon of the same material, I must ask you to believe it's the same material, you'll see some evidence for that later, in a moment, and put it in here, watch not too closely, magnesium, of course, and the small dimension allows the rate of reaction, which depends on the surface, to become large for each gram of magnesium. So the magnesium oxidizes rapidly. When it oxidizes rapidly, the heat can't leave fast enough. It gets very hot, and it glows brightly to us. But that's only a change in scale. It is not a change in the chemistry in any other way. I will prove that, if I get the right bar, by scraping a bar onto a piece of paper. Now, this is a bar of the same. I don't use the original bar because it's too hot to hold. But I use another bar just like it, and I file down and I simply make some small bits. That's all I'm doing, is making small bits of this magnesium bar out of the large bar. I am changing the characteristic size L, therefore I'm very much increasing the surface for the given amount of volume. Now, what would you call those little specks on the paper? Can anyone invent a name which will describe it? I want to see if you, yes? Filings, very good. These are just magnesium filings, no more. Pure magnesium, I didn't change it. Now I'm going to put it into the flame. You know what will happen, watch. Do you see those little bright sparks? Well, of course, I'm too impatient in a short lecture to make very many sparks, but in order to show you if I were simply filing for a long time, I would be able to do much better than that. So watch everything. I will now produce more filings and put them into the flame. It really has a splendid look. That's an example of the great energy release that can come when you have finely divided materials. Very often, mills handling flour and starch, which we think is perfectly non-explosive common materials. Yes, they're inflammable, to be sure. You can burn a piece of bread, but you cannot easily expect it to go up in a flash. Yet mills have exploded because the finely divided materials reacted so rapidly with the air that the explosion was capable of an explosion. Here we have another simple set of materials. Thank you. To show again the effective surface, I'll take a beaker, and this is simply what I've been told is a kind of lemonade. Wow. It really worked. And I think we'd refrigerate it better at home. It makes bubbles. In fact, the bubbles, of course, themselves are a place where gas is formed. The bubble, to begin with, a tiny sphere, must have a very large surface for its volumes. It's very small. It's very hard for it to form that surface, because how can it make so much surface? Surface is hard to make underwater, to make a fresh surface. As you know, that's the surface tension effect. And therefore, bubbles start not everywhere. It doesn't evaporate all at once, but at little places where there is a chance for a bubble to have a beginning, some scratch or edge or imperfection. And if I drop in a stone, it doesn't react with it chemically at all, it will make a few bubbles go. But not so very many. The stone brings in many little edges and surfaces. But if instead I bring in some sand, which you admit chemically is not going to do much to the lemonade, The sand has a truly splendid effect. A little bit of sand makes a huge head and foam because I'm pouring in so much surface, and in all that surface there are some chances to form bubbles. A very typical effect of a very great difference in surface. Let me see what this is like. Now I think we're in a position for the most spectacular performance of the afternoon, the traveling mouse Beatrice. I understand that a Christmas, is it that the right name? Thank you very much. It leaked out. This performer wanted to remain anonymous, but somehow or other the name leaked out. Mary, if you will start Beatrice going, we'll describe what she is doing. This brave mouse, who's been carefully trained by our RI assistant, Poor Beatrice. She's done beautifully. Do you think you really want to make her push that up again? Want to do it? Yes. All right, I'm not sure. She's got to work twice. That heavy weight with her nose all the way up the smooth inclined tube. Look at that, a sterling performance. Thank you. This ball weighs about half as much as Beatrice does. And now we're going to weigh Beatrice herself because we want to examine the question of what is this relationship between food and weight, which the Lilliputian mathematicians had not yet understood. So we'll proceed. I'm going to make a table and list a few animals as to the weight of food per day and the weight of the animal. And I shall try to use one set of units just so I can remember them well, and it will go. Now, how much does Beatrice weigh this afternoon? 13 grams, very good. And before I think you've studied her habits and you have a sample of her food, we might have somebody help you, Bill. Do you want to ask, can we ask that young man to help you? What do you see?
10.
The light interferes with the scale.
7 grams. 7 grams.
7 grams, thank you. That's the food per day is 7 grams. Now, already from this one measurement, you begin to see where the Lilliputian mathematicians were in trouble. If the mouse eats 7 grams of dried food, because that's a rather dry-looking meal. I'm not sure, it's a little bit like breakfast cereal. I'm not sure I would like to subsist entirely in breakfast cereal, but Beatrice will do it, and moreover, be a circus performer as well. I think that it's pretty hard to imagine myself eating half my weight, or you eating half your weight in food per day. You couldn't do it. You'd have to sit at the table all day long, and not much chance for sleep either. Wake up, it's midnight, time for another meal. That would be a very difficult economy indeed. So we begin to notice small animals are very hungry, and that is the case. It would be the case for the Lilliputians too. And it's by no means true that Gulliver could have eaten 1,728 of their meals. Now, let us try another animal. Now, I want to try animals that are comparable. By comparable, of course, I don't mean that there are the same number of claws. We're not studying claws, are we? We're studying the inner energy relations, the deep fundamental things about animals. And therefore, what I would like to take are all mammals, which have about the same economy, as Swift would have put it, the same warm blood, the same heart, the same lungs, but just differently scaled, and of course with many cunning and delicate engineering differences, but we don't have to discuss those. So, Anthony, I think you're going to help us by being the second mammal in this interesting scale, and much the most important. I write down boy, which is a reasonable identification. How much do you weigh, Anthony, today?
About 7 stones.
7 stones. Please, if I use stones, I shall be ever confused. Put it in kilograms, and I'm your man.
About 45 kilograms.
45 kilos. Very good. Thank you very much, Tony. 45 times 10 to the 3. 45,000 grams. That's a lot more. And now we have to examine what his rations might be. So we're prepared to weigh his luncheon. Now, we didn't make him... Here's Mr. Ian Gale with a splendid set of 3 meals, and Anthony has agreed that while maybe they're not exactly what he would choose, he would accept them. And here we go. We're going to weigh breakfast, which I see a pair of eggs, oatmeal, bacon, a substantial meal. And we'll get the data on this quite soon. Can be fairly approximate. We don't need much detail.
750 grams.
Very good. Somebody will keep that in mind. I'll try to write it down too. 0.75 kilograms. And now we have a luncheon with sausage and mash, I think that's called here.
Well, it's virtually a kilogram.
Very good, a
1,000
kilogram.
grams.
That's better. It's a substantial luncheon. And now a third meal, whether it's a high tea or an early supper, I'm not sure. You will be more experienced in these matters.
About 710 grams.
All right, about 0.7 grams. So I get 2.4 kilograms nearly, and we know from earlier work that there are about
weighs 340 grams.
Yes, about 3 trays to a kilogram. Very neatly arranged. Thank you very much. And that's about 1.4 kilograms for this ration. Now again, you notice the situation. 1.4 kilograms, or 1.4 times 10 to the 3, 1.4 to 45. That's about 1/30th or a little bit more of his weight, whereas the mouse was at 1/2 of his weight. And more than that, Anthony's food was not dried. If we dried it out and put it in a hard box of emergency yachtsmen's or mountaineers' rations, it would weigh still less. We haven't counted the water, which is of course not part of the energy contents at all, though it's an indispensable part of the diet. We don't need to count it because we're talking about energy relations. So that's what we have. And now, of course, what we'd like to do is to read the weight and examine the diet of a large mammal. And what I would really like to have is a whale, because that's a really splendidly large one, but we couldn't bring him in. And so we settled for something smaller. In fact, I have to admit, we weren't able to bring him in either. But he is very glorious, and we have brought him all but in by having him appear on film. And there he is at the Weights and Measures office, this splendid horse, complete with rider, the guardsman bringing this fine large horse to be weighed at the public weights office, where we can rely precisely upon the data that these people will obtain. Now the guardsman carefully dismounts. We have a public here, I see. And notice the guardsman is not being weighed. He's standing off the platform scale, but the horse is squarely upon it. And the weighman is now giving us the weights on those carefully inspected and graduated scales. And I think he's satisfied with the numbers he gets, and he's filling out a form, which form has been transmitted to us. So we have the certified weight of an excellent horse of the Queen's Guards, and I'm sure we have no more satisfactory large mammal to be found anywhere. And there's the form. And now when let us watch him leave. That's not a light, careless racing horse, but a substantial mammal of real consequence. Now they gave me the weight, and I shall read it off to you, I'm sorry to say, with a not complete understanding. The horse weighed 1,300 weight, 2 quarters, and 14 pounds. And when I discussed this with my consultants in Anglo-Saxon, we worked it all out, and it turns out that this horse, subtracting the 48 pounds of the equipment and harness, the horse weighs about 670 kilograms. And his food we can weigh. We have the food here, and I suppose you go ahead and weigh that. I have some earlier numbers, and I don't want to be too much delayed. This horse, thank you very much. This horse has a nice diet, which again is not all dried hay. That would be too bad indeed.
9 kilos.
Thank you very much. 9 kilos of hay, and I hope he isn't just, oh, very good, there's the real stuff. He has a few more kilos of oats, and everything works.
2.5 kilos of oats.
2.5 kilos. That's 12 kilograms of food. And now you begin to see the problem very clearly. This horse ate less than 1/60th of his weight in a day. The boy ate about a 30th or a 27th of his weight in a day. The mouse ate a half of his weight in a day. And this can be extended to many other animals, and now we can do the thing even more carefully. Let me first make one remark about the nature of the scale I'm going to show, and then we can examine it quite well. I want to show you a graph, but the graph is not the usual scale, and I must call your attention to that so you do not misunderstand. Usually I begin a graph scale, I write 0 here, then 1 unit, then 2, then 3. How have I proceeded? By adding. 1 plus 1 is 2, plus 1 is 3, plus an equal number is 4, and so on. That is called a straightforward or linear scale. We're quite familiar with that. But I have many reasons of mathematical kind, and also merely just to express a big range of numbers in a small space, where I proceed rather by multiplication, because you know a geometric progression rises much faster than an arithmetic one. I can't start with 0. If I multiply 0 by anything, I get nowhere. So I must start with something. I'll start with 1 unit. Then I multiply, say, by 10. I get to 10 there. Then an equal space for an equal, not an equal addition, but equal multiplication. So I get up to 100. 10 times again, and 10 times again, to 1,000, 10 to the 3, and 10 times again to 10 to the 4th. And so it goes. This kind of scale is a very useful scale because I can cover, without doing injustice to anybody, I can cover every range from 1 to 10,000. If I try to do that linearly, I must either have such tiny units I'll never see the ones at all, or I must go off and have this graph continue to sheerness, which is not very convenient. Let us then look at such a graph, thank you, Bill, prepared from a large experiment, which took many years and many investigators, doing the job that we have done with mouse, boy, and horse, but doing it still more carefully, because we really should take account of the heat value, the caloric value of the various foods. Isn't that true? It's really unfair to count toast and cheese and sugar and apple pie all in the same bland way. By the way, it's not all that bad. It's a good approximation, but it's only an approximation. It was like weighing the half ton of boys, which we just did by weighing a few of them and getting an average. Rough. Very good for estimates. Here's what, however, we've got for a mouse, rat, rabbit, dog, cow, whale, against the body weight all the way from a few grams to 100 tons, 10,000 kilos, more than 10,000 kilos. And this is the heat they used per day, or produced per day, going up here. And you notice the curve is quite tolerably, on this particular kind of scale, it is a quite tolerable straight line. It fits reasonably. Every time you have a straight line on this kind of a curve, it turns out that it's simple to represent, as you would believe, simple to represent in a formula what we see. And I shall simply mention that because we'll have occasion to use this formula on more than one time in future. The result is that the heat which a mammal must be provided with each day, which of course it loses each day because it doesn't end up with more than it began, is proportional to a little more than the 2/3 power of the weight. Heat goes like the weight to the, if it were 2/3, I remind you 2/3 equal to 0.67, and something a little more than that, 0.73. We shall say more about this in future lectures, because if it were W to the 2/3, W is proportional to V, the volume, V is proportional to L cubed, and L cubed to the 2/3 is just L squared. Now this is like the area. So the food you need is very, very approximately going up the amount per day like the area of the body. And that's not quite right because it isn't quite this, and we don't wish to say it is due to the fact that you lose heat by area, but essentially it comes down to the surface to volume ratio, the area to volume ratio we had before. And that's a most remarkable result and quite an interesting one. So this is the situation which governs animals, and we'll see that that makes a great difference determining, for example, which beasts can fly and which not, and determining what kind of food is available for which kind of animal and which not. For example, we've left off other warm-blooded animals, the birds, very beautifully and not so distantly different from our economy. The smallest warm-blooded animals that are really active are, I think, the hummingbirds. We happen to have a beautiful film of a hummingbird, which is being made in Bristol as part of a great investigation of hummingbirds. And I think when you look at this film now, there you see this bird flying, hovering in air, seeking from an artificial flower the unique food of the hummingbird. The hummingbird feeds almost exclusively. He does have a little protein supplement. Everybody needs that. But he feeds almost exclusively on honey, nectar, which is nothing but diluted honey. And a hummingbird will eat 2.5 grams of honey a day. Very good it is, too. Though he weighs only 3 grams a day, 8/10 of his weight per day in honey. Why do you think? Why do you think that a hummingbird is so ravenously after the nectar? Why doesn't he eat bird seed like any respectable bird would do?
Would he lose so much heat due to a small surface area ratio that you need so much more food?
That's right. He has to find that food which has the most energy content per gram. He can't beat this rule at all, but he can, twist it a little bit, bend it a little bit. So his success for bending it is to use a food which is the maximum richness. Otherwise, he'd have to stuff himself all day long with the dry seeds and would not succeed. Unless he uses very fatty foods or very energy-rich sugary foods, he cannot manage. So the smallest animals of warm-blooded nature must go after very energy-rich food because they're at the tail of this curve and they need so much heat per day. And compared to their size, that to catch it is extremely difficult. And so they've adapted to use this marvelous concentrated food. Now also, we have the problems of, I think I'm going to skip some things. Bill, I think I'm going to go through this rapidly, so watch your step. The problem of weight is an interesting problem. Everyone knows that a grape has a thin stem. A millet seed, bird seed on this millet, has a still thinner stem. You can hardly see it at all. And one may well ask the question, what determines the strength of stems that hold objects like fruits in place? This is now coming not to the question of energy at all, but to the question of structure, which we want to say something about as well. Because structure is equally important with function, with this dynamic, with the living function. Let us look at the melons. Thank you. Melons, of course, are splendid large fruit, and it is delightful to walk through the orchard of melons in the summertime, when the end toward harvest season, see the ripening melons on the boughs, and reach up and pluck a half-ripe melon and suck the juices from it. Have you ever done that? No. What is wrong with that story? Yes?
Melons grow on the ground.
Right, they grow on the ground. Why do you think they grow on the ground? You begin to have an idea? Let us say this there. Go ahead, just tell anybody.
Too heavy.
Too heavy, that's right. The stem to hold a melon would have to be proportionately larger than the stem that holds a grape by the ratio of the volumes to the strength of the stem. And the strength of the stem only goes as the area of the stem, because only the cross-section is what holds the next cross-section up. Therefore, you can't really have melons on a tree very easily. Some special trick would have to be developed. And I will show you a special trick if we can have this darkness and this particular slide. Here we see a famous melon tree of the tropics, grown in the West Indies and West Africa. I think it's a tropical example of a splendid tree. Lights, thank you. There you see, it is not a fake. It looks as if somebody has put rubber balloons or wax fruit or something and nailed it to a tree. This is obviously a large tropical tree, and those are obviously huge melons growing on it. They are, of course, not proper melons. They are called calabashes. Thank you, I think we can have lights. We have a calabash here. And you will say, how does it get around this? What is the trick? There's a calabash. I think you will understand at once. Now, this calabash has been treated, of course, as a dried one, but even in real life, there's only a little bit of a layer of soft stuff here, and the rest is mostly hollow, with a few fibers going in and among it. So the way it succeeds, the calabash fruit is big, yes, but it is not heavy. And that is one of the situations which evolution has developed. Now, to go further with structure, I'd like to have a couple of volunteers. Can you help out? I think we've had some practice. Let us, for the structure, try to see whether the penny is bent by the ruler. a scale penny, ordinary coin of the realm penny, and I think it works out well, as I recall, if we place this at 6.5, wasn't it so? Now can you do the rest for us? Somebody will hold that and place the penny on 11, and now let people see the deflection and take it off again and again. Does that heavy penny bend the ruler very much? Hardly at all. I see very little deflection. Would you say it was less than the thickness of a penny?
Yes.
Yes, I think it is less. Thank you very much. Let's try now a different scale penny to see what will happen. If we'll bring in the scale ruler and the scale penny, we will examine how structure works when scaled up. Thank you very much, boys. It's quite a load. Not very good. Six and a half. And now, Bill, if you can manage to... There's a marker to watch the deflection. Now, remember, it's a bigger thing. We expect it to go down maybe 12 times more, but take a look at it. It goes down enormously more. Much thicker than the thickness of a penny is the amount of deflection, several times that. The big ruler is weaker than the little ruler proportionately, by a considerable amount. You agree? Yes. Hold on tight so it doesn't fall. Thank you very much. Very good. So in general, this is true. Large structures are proportionately weaker than small ones. Bill. Thank you very much with the ruler. Bill, I'm going to strike the bones. I'm going to strike the bones. So next we want the pylon then. The dresses, I'm sorry. Let us look at a rather a very familiar object which you have seen before. This is a large structure of engineering sort, and it wants to be made big. Thank you. And our materials are only appropriate for this. Steel is the best we have. So we make steel structures, but I maintain that this is not a steel structure any more than a calabash is a melon. What is this structure? And this one. Characteristics, you see them everywhere. All bridges, skyscrapers, and so on. It's something like that. It's like the calabash. It's mostly empty air, cunningly fitted together and surrounded with steel. It doesn't have the density of steel. You couldn't manage with that, let alone the fact that you wouldn't have any room inside to live if it were a building. This is not a building, and yet the strongest and most economical way of building it is to mix the steel with air and thus reduce the density at the carefully arranging it so that the overall load is borne by the area, but the density is dropped so the weight does not go up proportionate to the volume because we have filled it full of air, and steel foamy structures are therefore much more practical, and all of the great structures that men have built almost invariably have that quality. If you look at them with sort of half-closed eyes, blurring out the image, you see a kind of shadowy thing there which is all solid, filled in. And that's the way one thinks of it. It's really a filled-in thing, but it's not made of steel any longer. If it's filled in, it's a mixture of steel and air. And that, I think, is at least one interesting way of regarding such structural steel production. And now, if we look at another structure which is less familiar, I think you have a dress, Mary, a very handsome dress. Did you make that dress? No, I'm afraid it was made by a professional. It's very pretty. Now, this is not a common thing to do, but I'd like you to pay attention to it. Let us all look at it. Just let the dress fold over and drape smoothly onto the floor. You see, no strength in such a structure. Of course, it's quite flexible. But those of you who have made doll's dresses will observe that a doll's dress made of the same proportions, the same materials, is much stronger. Of course, it has not been scaled down in thickness. It's a typical example. If you keep the thickness the same and scale everything down, the structure becomes so strong that a dress will easily stand by itself. Thus, the problem of manufacturing lifelike dolls or lifelike puppets with lifelike costumes is most subtle and difficult. The scaling must be right, and it's very hard to do that. One can't get the proper materials. So I think that is interesting result. Now, the same thing happens repeatedly when we have to consider one more interaction of structures, of systems, physical systems, with the outside world. We've talked about heat and energy taken in as food, and you notice the relationship there is much more like an area than a volume one, and so the smaller objects have the larger need per unit weight, much larger. We talked about strength, which is really the resistance of the structures to the pull of gravity, the outside influence of gravity, which seeks out their weight. We've talked about heat and chemical reactions, the absorption of the villi of the stomach, the burning of the powders in the flame, the metallic powders in the flame. And the interaction with the air is one more place, air resistance to motion is one more place where the surface, where the outside is obviously very important. So let me describe what I mean by a parachute. And the parachute may often be seen falling from the sky, and when you see it, there it comes, thank you very much, Bill. And the parachutist is safe, but he would not have been safe if he had not done a clever thing way up when he began. What did he do? Yes, he did, but in our mathematical language, to show the connection of all these things. Made a bigger area, bigger surface area, caught more air, and that did the job. And of course, I can do exactly the same thing by, for example, if I toss out a piece of paper, I can't even make it go to the ground. It feels the air so strongly that its path is hard to predict, and it barely settles. But if I simply take the same weight and reduce its area substantially by making it not a thing with one small dimension and two large, but all three dimensions about equal, why then it plops down, no trouble at all. And of course you know this, but it's a very important thing, and very important in the design of everything that moves rapidly through the air, which is a topic we shall come to in the course of time. Very soon now, in fact. Now, I would like to talk in closing about one grand subject still that we have not discussed till now. This topic is the Earth itself. It's the biggest scale. So you've gone now on a scale talking about surfaces from the stereo scan ultramagnification of the probing electron beam right up to large structures and animals of any size. But we can go still farther. I'd like to talk a little bit about the Earth itself and the idea of the geological structures, the geological formations that we see in the world. Here are a couple of points that I want to make. First of all, we have a picture of a famous cave. This cave is the cave in Kentucky, the Mammoth Caverns of Kentucky they're called, and there are some odd tourists walking about, as I indeed have done, mouth open, looking at the wonder of this lighted limestone cave. And it's wonderful, I'm not denying that. I hope you all have a chance to see a great limestone cave. I think there must be some in Britain. I'm not sure of that. Are there some large limestone caves, caverns known to you? In any case, there are certainly some in southern Europe. Now, on the other hand, while it is large compared to a man and a sight worth looking at, it is not a large feature on the surface of the Earth. Not as big as a small world map in your schoolboy diary will not show any such cave marked on the map. It's a tiny feature. I don't think any one of them anywhere is as much as half a mile across. And that's only a pinprick to the surface of the Earth. Here is about as big, not quite a cave, it's a broken open cave. This is the crater of a splendid latent volcano near Guatemala City in Central America. Notice the beautiful slumping of the lava as it flowed, the ashes flowed to the sides, and here's this large collapsed bubble which once blew off, and then the walls collapsed clearly on one side, piled in. This thing is less than half a mile across, and it's about as big a hole in the ground as you'll easily find. Other holes in the ground either have very sloping sides. Even the Grand Canyon you can walk down the Grand Canyon, walk back up again. It's not a sheer cliff. It has cliffs of a few hundred feet, jumping off a few hundred or a few thousand feet at most. Nothing falling off 20 miles into the Earth in one sheer jump. Why not? Because the materials of the Earth are not strong enough on the scale at which the Earth exists. Again, the weight, the load, goes up like the cube of the dimensions, like the volume. the strength goes like the square, like the amount that supports each load, like the square of the dimensions. And therefore, just as our L cubed over L squared, the amount of weight per unit load goes as L, and sufficiently large L, you overwhelm the strength of even the strongest rocks. Therefore, the rocks are not strong. And to demonstrate that, it is enough to look at a relief map. Here is a very handsome, very attractive visual relief map, which we can see. And Britain is here, immersed in the sea. And the mountains, to be sure, exaggerated for relief. That's quite all right. But the materials of this map are celluloid, a plastic. And therefore the materials are, we don't call them strong, but on this scale they're prodigiously strong. For example, like, there cannot be any mountains in the earth 150 miles high, but I can easily produce an absurd mountain made of celluloid, which sits right in the middle of England, looking very foolish, 150 miles high. And indeed, it's not only a mountain, but at the same time it's a cavern. And you see, that's a cavern far more remarkable than anything that really exists. What is the trouble with that map from a mechanical point of view, the point of view of shapes and function? The trouble is plain. It is too strong, far too strong. The only proper material for a map must be one that will not allow me to make absurdly high mountains and absurdly large caverns. It must be a material that will allow the Earth to behave as weak as it really is. We have few such materials, but I think we have one of them. And we'll show you a relief map made in the mechanically most suitable material for relief maps themselves. Mr. Gale again is helping us. And here we have a relief map that is, I think, properly made. And to show you what I mean, I will try, for example, to erect a splendid, absurd mountain on the plains of the Midlands. No chance. The mountain dwindles away. If I try to make a tiny cavern, of course I can do that. That's very realistic. I can use my fingertip and make splendid canyons and caverns of a real size, but not of an unusual and bizarre one. But the rest I cannot do. This material, which as you recognize must be a very soft material, and in fact it's a cream which I can easily eat, is the right material, excuse me, is the right material to represent the strength of the Earth. The Earth on this scale, on the scale of a map, is not gigantically strong. It is in fact quite weak, and the best representation for it is something in soft whipped cream, in foam. Of course, the density is not quite right. It's only a rough approximation. The real Earth rocks are even weaker on this scale of this relief map than is the whipped cream. And that is the curious part of the lesson, which demonstrates to us once and for all how important scale is in determining the mechanical properties of substances. Thank you. Of appropriate pieces of landscape, if some of them come forward.